All right. So this first question looks a lot like a chapter 4 question, right? It is. It is. So you could do that first question just by using the unit circle. If you use the unit circle, you'd find that sine inverse of 1/2 is equal to pi over 6 or 5 pi over 6, correct? However, we have to worry about sine inverse. What is the, stop talking please. What is the range for sine inverse? Negative pi over 2 to positive pi over 2. So do we want both of these two answers that we retrieve from the unit circle? No. Because you notice that 5 pi over 2 is not inside of the range. However, pi over 6 is. So we have just one answer for this, pi over 6. Everybody okay with that idea? Okay? All right. So if I am going to do the second problem, if I want to solve for x, what am I going to do to get the x by itself? Well, I would do the sine inverse of both sides. Everybody okay here? Seems fine, right? No big deal. And then using the unit circle, we can say that x is equal to pi over 6 or 5 pi over 6. Do we want to take both of these answers? Yes. Why is it? Okay, again, I'm going to explain why, so don't get too frustrated yet. It's supposed to feel, it's, okay. So the reason I'm approaching it this way is because I know this feels not intuitive, right? We did something that looked almost identical one way, and now we're doing something different and we're not doing it the same way, right? I want to explain that because, again, the natural instinct would be, yeah, it's the same thing. You just have one answer, right? These are two fundamentally different questions, though. So here, in the first question, we're just asking to evaluate sine inverse of 1/2. Based on our definition of sine inverse, that has only one answer. In the second question, we're looking for the values of x that evaluate to 1/2 when you take the sine of them. That's going to include the one answer that's the output for sine inverse, but it could include many, many, many other things. In fact, each of these are answers, but there's more. In fact, there's infinitely many more. What's another possible answer? If I add 2 pi to each of these and find an angle that's coterminal to it, those would both be answers. So 13 pi over 6 and 17 pi over 6 would also be answers. And you could add 2 pi to each of those and get another pair of answers. And here's the thing, Bella, is that we're not asking to evaluate sine inverse and find the answer. We're looking for the values of x that when I take the sine of it, I get 1/2. Now I'm going to use that sine inverse to kind of find the values that I might be interested in. But I have to, it's a fundamentally different question, right? Here we're plugging values in for x that give us 1/2.
Oh, we're not finding that. Wait, we are finding.
We are finding x. And there's infinitely many of those x's that do that.
Yeah.
Right?
Equal 1/2.
That would evaluate out to 1/2 when you take the sine of them. Right? And we can find them, stop talking please. We can find them by using the inverse to locate, or the unit circle, to locate the values that we're interested in.
Okay.
And then we can just keep adding 2 pi to those answers to generate infinitely many of them.
Oh. So you don't have to obviously write them all because there's so many.
And we are, well, we are going to talk about how to write those solution sets, because often what we're going to do is we're going to specify a range of values that we want the answers inside of. Or in the case that we want all the possible answers, we'll invent a notation that will allow us to write those infinite number of solutions in like a formulaic sense. Okay? So let's look at this specific example. So let's say that we want to solve cosine squared x equal to 1 for x in the interval 0 to 2 pi. So here we've specifying where or what answers we want. We don't want infinitely many of them. We just want the ones that are between 0 and 2 pi, right? Okay, so we'll start by solving cosine squared x equal to 1. What's the first thing I need to do in order to solve this? I need to square root both sides, because I can't do cosine inverse when there's a squared on there. I need to get rid of that. What do I have to remember when I square both sides? I get plus or minus, and the square root of 1 is just 1. So I can now split this off into 2 equations. Cosine x of 1, or I'm sorry, cosine x equals 1, and cosine x equals negative 1. Everybody's okay there? So if I then take the cosine inverse of both sides, I get that x is equal to the cosine inverse of 1 and the cosine inverse of negative 1. So I could do that on my calculator, or I can try to do this on the unit circle. I recognize these are unit circle values for cosine. So I know that we have the point cosine is equal to the x coordinate. So I have one answer here when cosine is equal to 1 that occurs at 0. And then I have another answer over here where cosine of x is equal to negative 1. There, x is pi. Everybody okay with that idea? Okay. So I notice here that 0 is in the desired interval, and pi is also in the desired interval. So those are both solutions. I now also need to check if there's any others than these. If I find an answer that's coterminal to 0, I would get that by adding or subtracting 2 pi, correct? Would that be in the interval? If I add 2 pi, I would get 2 pi, which is not in the interval 0 to 2 pi, because notice the parenthesis means we're not including that endpoint. So that's not in there. So the best we can do on 0 is just 0. How about x equals pi? Can we get another coterminal angle to that inside the range? No. So those are it. Those are my 2 solutions. Everybody okay with that idea? We're good why there's no more? Let's do another. Again, so my answers here are just 0 and pi, right? That's it. Everybody's okay here? So we're going to solve for x. 3 times tangent squared x equals 1. And the answers we're looking for are between 0 and 2 pi. Yes, Raul? Certainly. So what should we do first on this one? I would divide by 3 first and then get rid of the squared. Yep, so those are the first 2 things we need to do. Usually it's easiest to do it in this order where you get rid of the constant first and then take care of this exponent second. Remember though, when we square root both sides of an equation, what do we have to remember? Plus or minus. Now, at first glance, this doesn't look like a unit circle value for tangent, but if I do a little bit better here, I know that to square root a fraction, that's the same thing as square rooting the numerator and denominator. The square root of 1 is 1, and the square root of 3 we can't do anything with. And we probably want to do what to this? Rationalize the denominator to get to there, right? So now I'm going to use the unit circle. Well, actually, let's say something first. So this now I'm going to split into 2 pieces. Tan theta is positive, or I'm sorry, tan of x is equal to positive root 3 over 3. And then tan x is equal to negative root 3 over 3. Everybody's okay with that? And we'll take tan inverse of both sides. And we're here. So far, so good? Okay. What I'm going to do now is I'm going to go to my unit circle and look for places where I get these values for tangent. Does anybody see where we get root 3 over 3 on the unit circle for tangent? So you say pi over 6, okay. So to evaluate tangent, we do y over x. So just as a little aside here. So that's going to be 1/2 over square root 3 over 2. So when I multiply by the reciprocal, I get 1 over root 3, which is what we want, right? Everybody agree with that? So one of our values for x is going to be pi over 6. Okay, let's go back to the unit circle and look for any more. Where else would I see 1? How about here at where I have a y coordinate of -1/2 and then the square root of 3 over 2? Right? That would work, wouldn't it? The same thing will happen, but I'll get -1 over root 3. Okay, so that's another spot. And then where else? Here at 7 pi over 6. And then here at 11 pi over 6. Everybody agree with that? So we have 5 pi over 6 for here. We had 7 pi over 6 over here, and then 11 pi over 6 over there. Now, my next question is this all of them? Well, remember our answers had to be between 0 and 2 pi. Is this all of them then? Well, if I add 2 pi to any of these things, since they're all positive, they're all going to be bigger than 2 pi, right? Everybody agree with that? If I subtract 2 pi from any of these, since they're all positive, if I subtract 2 pi, I get a negative for all of them, right? So if my answers are between 0 and 2 pi, if I pull everything from the unit circle, would I ever be able to get other answers? Yeah, there is, but we'll deal with that a little bit later. Well, that is at the end of this section, we'll deal with that case, but it's rare. But we'll explain to you why that can still happen. So you do have to be a little bit careful. And it has to do basically if there's a transformation that changes the period of my function, where I can get more than one period in between 0 and 2 pi. Remember when we graph things? So you can still happen. And Andrew, to answer your question, if the coefficient on the x is 1, you can't. If the coefficient on the x is not 1, you could get more or less answers than your unit circle. In fact, in the homework I have, when I give you the solving problems, there's 4 different ranges to solve each problem with. So you get some practice looking for some other places. And we'll do some examples here coming on what we'll go back and like change the range of answers and show you how you can, what you need to do to deal with that. Okay. Yeah, there's like almost nothing down. Okay. Yeah, we just evaluated tangent of pi over 6 to check to see if that was the one we were looking for.
And it was. And we know it was because it was here.
Well, it's because we got root 1 over root 3, which is what we're looking for. Yeah, Andrew said that pi over 6 is one of the answers, and we just checked really quick to make sure that tangent of pi over 6 gives me the right answer. That's all we did there. All right. So this is the last solving example we'll do today. We'll go back and after this one and look at each one of our answers that we did, each one of these examples, and do the same problem using like some different ranges of x to show you how you can manipulate our unit circle answers to answer other ranges of questions. Okay? And then we'll worry about the ones where you can get more or less answers than your unit circle stuff next time. All right, so to solve this guy, what are we going to have to do? Yes. Can we do it a little bit later? Okay. So what do we want to do to solve this? I mean, you can, but it's not going to help you solve anything. I would not do that. What if I just imagine y to be equal to cosine x? So what if I just replace cosine x with the variable y? That equation then becomes 2y squared plus y minus 1 equal to 0. How would I solve that equation? What else could you do? No. Or you could use the quadratic formula here. So, stop talking, please. To factor something like this, we need to find two numbers that multiply to give me a times c and add to give me b. Stop talking, please, unless you're answering my question directly. What is the value for a here? 2. What is the value for c? Okay. And what is the value for b? 1, right? What are the two numbers that multiply to give me negative 2 and add to give me positive 1? this is taking entirely too long. Multiply to give me negative 2. Add to give me positive 1 is 2 and negative 1. So when I have, can we seriously stop? Okay, shut up and listen, please. Because negative 2 plus 1 adds to give you negative 1, not positive 1. It doesn't satisfy the two questions. Now that I've done that, I'm going to break up the 1y into 2y plus a negative 1y. And then I'm going to make my two groups. From the first group, I can take a greatest common factor of 2y. That leaves me with y plus 1. From the second group, I can take a greatest common factor of negative 1. That leaves me with y plus 1. Notice now that each of these have a y plus 1 in common. So if I factor the y plus 1 off, I'm left with 2y minus 1 equal to 0. Ella. I can then set each of these pieces equal to 0 and solve. Right? And now I'm done. Right? No, what are we trying to solve for in this? What are we trying to solve for in this problem? We're trying to solve for x. So I need to substitute back in cosine x, which was what y is equal to. So I will take the cosine inverse of each side. And now I'll go to the unit circle to retrieve the values. So where is cosine equal to negative 1? It's at pi. Where is cosine equal to 1/2? It was, I think it's pi over 3, right? Let's double check real quick. Yeah, pi over 3. And where else? 5 pi over 3. So my answers then would be pi over 3, pi, and 5 pi over 3. Everybody okay there? All right. That's your final answer. Yes. All right. We're going to now go back through these 3 examples that we've done and show you how to take our answers from 0 to 2 pi and get answers in like different ranges. So we're not going to redo the solving. All we're going to do is kind of take the answer that we got from 0 to 2 pi and change it around so that it fits. Okay? So what if I wanted to go from, instead, my answer to be 2 pi to 4 pi? I'm not going to do anything different until I get to my final answer. And I'm just going to add 2 pi to each of these. Everybody okay with that? That's easy, right? What if for this one we wanted to go from negative 2 pi to positive 2 pi? Oops. Here we're going to get twice the number of solutions, right? So each one of these 4 are still solutions, but I also get a second set when I subtract 2 pi from each of these. So I'm going to get 8 answers. So I'm going to have my 4 positive ones. And then I'm also going to get negative 11 pi over 6 from this one. I'll get negative 5 pi over 6 from the next one. I'll get negative 7 pi over 6 from that one. And negative pi over 6 from that one. Everybody okay with that? And then for this last example, we're going to write our answer over the entire real line. Okay? So how many answers are we going to get? Infinitely many. So we're not going to be able to list them all. What we're going to do is we're going to describe what that looks like. Okay? So let's do that. So one set of answers is going to come from pi over 2, and then plus any multiple of 2 pi added or subtracted from that, right? So I'm going to say 2 pi k, where k is an integer, right? So the integer values of k would be like 1, 2, 3, 4, 5, or negative 1, negative 2, negative 3, negative... Riley. Thanks. Similarly, we can do this. And that. Everybody okay with that idea?
I'm not.
Ask your question, Isabel.
Yeah.
So, what are we saying with this? This is saying pi over 2, or pi over 3, and then you can have pi over 3 plus 2 pi times 1, pi over 3 plus 2 pi times 2, pi over 3 plus 2 pi times 3, as well as like pi over 3 plus 2 pi times negative 1, pi over 3, no, keep on going. Keep on going. For all values, all integer values, plus 2 pi times negative 2, etc. So what is that giving us? It's describing all the angles that are coterminal to pi over 3. So that's all that plus 2 pi k is doing. So it's because we can't list the infinitely many of them. We're just going to describe them as like a set. Yeah. All right. For next time, what I'd like for you guys to work on . I don't know. I haven't thought about Monday yet.
Oh,
So, yes. Sure. So keep in mind, make sure you read the directions. Each of these have an A, B, C, and D. Well, here's the thing, Ann, is you're right, but once you've done part A, getting parts B, C, and D are not difficult, right? The hard work is getting A, and once you have A, you can write the rest of them pretty easily. So it does look like 64. It's really just like 16 problems, though. You have 64 answers, sure. But you guys saw how quickly we did, like, once you have the answer for 0 to 2 pi, how easy it is to get the other ones. We still have 20 minutes left of class.